So today our topic is nitrogen dynamic and forage quality. So in APSIM Lucerne model, so the model structure is separate in leaf, stem, and root. So that's what we had here. So this is the typical leaf structure of nitrogen demand, which include all those components. So our objective is to get a maximal nitrogen concentration, critical nitrogen concentration, and minimal nitrogen concentration for each organ. So for let's start with the minimal. So the minimum concentration, nitrogen concentration, is the structural tissue, the nitrogen in the structural tissue, which is the concentration of the dead material. So those nitrogen are not moving within that organ or among other organs. So the critical nitrogen concentration is the amount of nitrogen is needed for plant to function, which is not limited for growth. The maximal nitrogen concentration is the upper limit for nitrogen storage. So that's above, that's the maximal nitrogen concentration that each organ can reach. Okay, cool. Once we have that, so again, in APSIM, both carbon and nitrogen has two components. It's more like you have a nitrogen supply and demand that will go to each organ, leaf, stem, and roots. So as the carbon supply was through light inception, which we covered in the second day, and dry matter demand was through the third day of how leaf, stem, and root demand the carbon that being made through photosynthesis process. So for nitrogen, it's the same story. So nitrogen supply was from nitrogen uptake and nitrogen fixation. So here, because we didn't measure those two processes directly, so what we thought was, okay, we have our total nitrogen from stem, leaf, and the roots. So we can calculate them together, and we have our total biomass. So the relationship between total nitrogen and total biomass is a very strong linear relationship. So overall, the nitrogen concentration is about 2% as a Lucerne plant for any Lucerne plant.
And I'll just jump in there to clarify a couple of points. So when we were measuring roots, we were measuring to the depth of about 30 centimeters. So it was a spade spit that we were going down to. So it's not the total root nitrogen, but we figured we captured most of the remobilizable nitrogen that would be available. So that's one point. The second is, in none of our experiments have we measured nitrogen fixation or done any N15 work. So we're working off the biomass nitrogen values that we collected, and in a non-limiting situation, trying to ensure that the plant, when we're looking at it, that there is no limitation to the nitrogen available. They were growing under high fertility irrigated conditions, so we don't expect N fixation to have been compromised during these experiments.
For nitrogen supply, we used the up boundary of this regression points to make sure none of our treatment was nitrogen deficient, which is 0.25. So 2.5% of nitrogen concentration was applied for total biomass being made from the photosynthesis process. This is a shoot nitrogen dilution curve. So our shoot nitrogen concentration and shoot biomass. So this is what typically being used for analysis. However, for APSIM, we have to divide that into leaf and stem. So if we look at leaf nitrogen, the maximal is about 7, although those points are probably 6.5. And the minimal leaf nitrogen concentration is about 3.5% for all the experiments that we had. So this include 84 days treatment and also 28-day treatment. So in increasing, decreasing photoperiod, the range didn't change much. Although in decreasing photoperiod, there's high leaf nitrogen concentration values being found. If we implement that into the model, we use the nitrogen dilution curve. So for 0, it's 0.08, which is a bit higher than 0.06 to get the curve to fit what we presented in the previous slides. So for stem nitrogen dilution curve, showed a similar curve as the shoot nitrogen concentration. The shoot nitrogen dilution curve was more contributed by stem nitrogen changing rather than the leaf nitrogen changing over time. So here's how we model the stem nitrogen concentration in the stem organ. So when we come to nitrogen in the root, so this is measured root nitrogen percentage and over time. So it showed a very strong seasonal pattern. Root nitrogen decreases in spring and recharge back in the autumn, which is the same pattern that we found for root biomass. So for 84 days, it has higher root nitrogen concentration than 42 days than 84 days.
So I just wanted to point out for those that have joined us today, the 3 treatments here. The short one I said earlier was designed to create stress for the plants, so defoliated very quickly. The 42, or the LL, is sort of around what we would call normal management here for us. So that's about 350 thermal units being accumulated. The 84-day, it's 3 months that we're leaving the crop in the ground. So we were really trying to see, if you just leave an alfalfa crop for a long period of time, what will it do? And that's what that treatment was designed for. And for us, it was quite intriguing to see that its nitrogen dynamics showed the same seasonal patterns that we've been picking up before, but the levels were obviously much higher. So the plant was able to retain a whole lot more nitrogen. Okay, so that's really what we wanted to see, those differences in the treatments, because that's what we actually designed the treatments for, to try and see whether we could change the dynamics. And yesterday, when we were showing the biomass, we were showing that actually that 84-day treatment in that cycling was producing up to 10 tons of biomass below ground in that top 30 centimeters, whereas the others, the short one, was down at close to structural, so close to 2.5 tons. So there was 7.5 tons of biomass in 30 centimeters. So this plant is doing a huge amount of remobilization through the season in our environment. Okay, so it just gives you an idea of what's happening. And I think yesterday Xiumei said that some of the previous work, and it might be yours, Jeff, showed that a lot of that remobilization that's occurring is nitrogen rather than carbon. That what you're finding in the shoots is about 25%, I think, was nitrogen and 12.5% was carbon. Mm-hmm. So it was very good for us to be able to see those N percentages following exactly the same pattern as the carbon that we described yesterday.
So yes, yesterday we mentioned remobilization. So remobilization was more of nitrogen remobilization to help shoot regrowth after defoliation. So for nitrogen remobilization, we tested 8 different values for nitrogen remobilization coefficient and see which one fit the best. So 2% gives us the best fit. So I didn't test the remobilization duration, which is from yesterday's talk, because remobilization duration should be the same as happens in carbon remobilization. So in this exercise, we just use the same remobilization duration for nitrogen.
Please, just one point. Be careful with expressing nitrogen concentration. because nitrogen concentration can be varied not only through nitrogen remobilisation, but also through carbohydrate accumulation. So it should be better to express your data in nitrogen content in root. For example, the root nitrogen percent can vary both by nitrogen accumulation or diminish by soluble carbon accumulation. As root are the both component, nitrogen and carbohydrate, so nitrogen concentration is not a good image of the nitrogen fluxes. It should be better to express the nitrogen quantity in root, absolute quantity, and to see after how this quantity vary by remobilisation and accumulation, and then the result in terms of nitrogen concentration is also affected by simultaneous accumulation or loss of water-soluble carbohydrates. You will have a better image of the nitrogen movement by using only the nitrogen quantity in the root.
Yep, and we can calculate that and have calculated that as the total amount of N that's being shifted. For the modeling, we needed a value that you can use. And so the 2% value worked reasonably well. But I take your point, if this is in line with the biomass that we had yesterday. So it's a percentage of the biomass that's there. So it is actually a multiplier by the time you can get those values out from the multiplication of those that's coming in here.
Just to underline the difficulties in interpreting nitrogen concentration.
Absolutely.
You need absolutely to refer to the size of the box.
Yes, and in the 84-day treatment, as I said, we're dealing with 10 tonne of biomass, whereas in the short treatment we're dealing with 2 tonne of biomass. So we have calculated those kilograms of nitrogen that are being remobilized from that 2% value. Yeah.
And so if we put that 2% nitrogen remobilization coefficient into the model, so we had an overall fair leaf nitrogen concentration prediction, and also good overall stem nitrogen prediction, and a fair root nitrogen prediction. So implement nitrogen concentration values into the model actually helped shoot and root biomass simulation. So overall, our shoot and root both showed a good agreement. So from the previous slides, we conclude here, average shoot and root dry matter has about 2.5% of nitrogen. Root as a reserve organ showed the strong seasonal pattern, and its nitrogen concentration differed with defoliation treatment. APSIM Lucerne model have a fair to good prediction of leaf nitrogen, stem nitrogen, and root nitrogen. Fitting nitrogen improved dry matter prediction, especially under 28 days defoliation treatment. So our future work, so if you remember from yesterday's talk, we said root maintenance respiration was mainly because there's remobilized of nitrogen. Therefore, root respires more in spring and also in early regrowth cycle. So if we can link root nitrogen, either concentration or absolute amount, like Jill said, if we can link those two together to improve the model fit of shoot and root biomass, and also shoot nitrogen and nitrogen concentration of those organs. To do that, we probably need to conduct a optimization process for both carbon and nitrogen remobilization parameters for 3 full dormancy classes.
Are there any questions or other comments for what we've done so far?
I just want to come back to the first and second slide, please.
Yep.
If we can think that we have a linear regression, so this coefficient should not be different from 0. So we have a strict proportionality in total N input and total carbon input, total biomass. So it's very clear, and it's a very general result obtained in Lucerne in perennial plant. Very good. But when we go to the dilution curves, the dilution curves indicate that the accumulation of nitrogen in shoot is less proportional than the accumulation of carbon, of dry matter. So if we have such a curve in shoot, we should have a reverse curve for the root to have a constant nitrogen versus carbon input. So it is very fascinating that we have a symmetrical and opposite between dilution of nitrogen in shoot. As the shoot grow faster, the nitrogen decline. The nitrogen for any new dry matter is less and less, while for root, it is the reverse.
Yeah.
It is very fascinating.
Yeah.
For me, the plant is very strongly organized.
Yes. And those relationships, the next one with the stem, I think it is the stem. The stem, the main change is coming in the stem, which fits beautifully with our ideas of structural carbon. So the dilution is actually from structural carbon. As we get more lignin, as we have to hold the plant up taller and taller, it's the stem component that's changing its nitrogen concentration, whereas the leaf component was, holding its N concentration very strongly between 3.5 and 6, but mostly around sort of 4.5 to 5% N. Yeah. So as the stem component was doing most of that change, that gave us that dilution curve in the shoot biomass.
Here, it should be very interesting to understand why the blue points are very low. Some treatments are very different each other.
Yeah, and that was part of the treatment design. So those treatments, as I explained yesterday, were designed to be the equivalent of set stocking grasses, that you're constantly removing the leaf too quickly.
Yes.
And so the plant becomes short of carbon and therefore spends more of its time trying to produce leaves. But we were defoliating that about as frequently as you could, and not allowing it to actually get any partitioning to roots. So it was being defoliated after about every 200 thermal units.
Yes.
And so it wasn't, Xiumei's just about to show you the root biomass data from yesterday. So the blue dots are actually the grey dots in this diagram here.
Yes.
And you can see that it was really designed to deplete it of its reserves and see how the plant would respond. And so that part of that response is a dilution of the nitrogen concentrations. And so that crop actually collapsed more quickly, as you would expect. And when it was an FT10, it collapsed even quicker. But for us, the interesting thing here is what the 84-day treatment was doing, which is producing 8 to 10 ton of of root biomass. And of that root biomass, about 2% of it was nitrogen, and that was relatively consistent. Are there any other comments, or we'll move on to the last part of what Xiumei's got?
A short question in the Derek and Xiumei.
Yes.
In the just to be sure about I understood in the first slide, the slide that Gilles asked you about biomass and nitrogen.
Yes.
Just that. This is the biomass is leaves plus stem plus root.
Plus, yes.
Yes.
Okay. Thank you. Thank you.
Yes. In other words, if you have measured all the biomass, this axis, the axis total biomass, is a carbon fixation, more or less,
Yeah.
is a accumulation of new carbon, is a carbon fixation.
Yeah.
And the total nitrogen is a total nitrogen fixation on assimilation. You have a picture of how much nitrogen is associated with carbon. If you enter more carbon, you enter more nitrogen. The dilution doesn't exist at the whole plant. The dilution is only a problem of shoot. It's not a problem of whole plant.
It's zinc limited in aerial part, so it's
yes. It's a very good demonstration that the input of carbon, of nitrogen, are strictly proportional.
Yes.
As you increase the input in carbon, you increase the input in nitrogen, and vice versa.
Yeah.
The shoot level, you use less and less nitrogen per unit of carbon in shoot.
Yeah. And the assumption we're making here was that we're never nitrogen limited, and so nitrogen fixation is happening. And if we look at a lot of the work on nitrogen fixation, it would suggest that you get about 25 kilos of nitrogen per ton of legume that you grow. So the numbers started to match up quite nicely with a lot of the work that Mark Peoples has done on N fixation. So yeah, those relationships hold, and they were quite strong. Yeah. So the assumption we were making here was that we have no N limitation.
But the figure showing stem and nitrogen concentration shows stem, yes.
Yep.
Show that for similar biomass of stem, the blue points are
yes,
with lower nitrogen concentration. So something happened there.
So the problem is there is because the plant is limiting in nitrogen, or is because this stem are not the same, have not the same structure, more lignin or more whatever, I don't know. For me, I suppose the blue treatment should have caused a nitrogen limitation.
Yes.
A nitrogen fixation limitation. Because of two frequency of cut.
Absolutely.
Yeah.
And the two frequency, remember, we've assumed that we have no nitrogen limitation, but all of our data has shown that that 28-day treatment created a nitrogen limitation. So had we measured nitrogen fixation, then I suspect we would have seen a reduction in N fixation occurring. If you assume that 10% of the carbon on any given day is required for N fixation, what we've got here is a reduction in N fixation. And so over time, that became more and more of a problem. as the treatments went on, which is exactly what we designed the treatment to do, but we just didn't have the resources to do the end fixation work with it. But it was there, and in all of the data that we've shown, that frequent, it follows all of our grass physiology as well. If you cut too frequently, you're carbon limited, so you try and produce leaves, so your roots become less, so you have less nitrogen available, and it becomes a negative feedback. And that's exactly what happened here. And what happened more, it happened more frequently and worse for the FT10 cultivar. For that cultivar that spends less of its time partitioning to roots, it collapsed most quickly under this treatment. Yeah, and it's the lack of nitrogen in the system that did that, we suspect. Yeah.
Yes, and moreover, for legumes, nitrogen fixation is very highly dependent on photosynthesis. So too rapid defoliation would impair the nitrogen fixation. And probably if you have the slide with nitrogen dilution in the wool, you can see that this blue, the blue line, this line is very close to the critical curves we have already established in France. So it's very, very close. Probably not this, the curve probably will be there. So here we have probably data point with limiting nitrogen, with for which the nitrogen fixation is limiting. It should be interesting here to draw the critical curves. Probably is I remember it's exactly the same coefficient here, but here it would be 4, 4, 8. So it should be something like that. Here. So all the points below these critical curves should indicate that the plant has not its optimum, its critical nitrogen nutrition. And probably it is mainly the data of blue point and some other data. I don't remember what is this treatment, what are these treatments.
That's 84 days cutting.
Yes.
Yeah, so some of those treatments that are below the line were also the treatments that were left for a long time, and so they started to lodge and senesce.
Perhaps lodging and senescence, yes.
Yeah, so as you get higher up in those biomass levels, when you've got 8, 9 ton of biomass, that's senescence that you're kicking in from those treatments. Yeah.
Yes, it should be very important to make a very careful interpretation of each data point according to the system. Yes.
Yeah. Okay. I think we'll stop at that point and just move on to the next part of what Xiumei's got.
So we move on to leaf crude protein. So since we predict or we simulate leaf nitrogen concentration, so times 6.25, that will give you leaf and stem crude protein. So here the simulation results is very similar to what leaf nitrogen concentration simulation results.
Sure.
Yeah. So we have HH, LL, SS, so different defoliation treatment, and FD2, 5, and 10. So the range of leaf crude protein is between 30 to 35 for most of the treatment. So although the range is small, but the prediction still needs to be improved. Cool. So So then the stem crude protein is the same story as stem nitrogen. So showed all the treatment showed fair to good prediction. Again, it's the 84 days, 42 and 28 days cutting 2, 5, 10 for dormancy cultivars. So we can see FD2 is not doing really well under 84 days cutting treatment, and so as FD10. FD10 under SS treatment, so 28 days treatment, we have overestimate of stem.
So what we don't have in the model at the moment is a negative feedback to be able to say that nitrogen fixation has been affected, and therefore we're overestimating under that FD10 regime, under the short regime, we're overestimating how much nitrogen we've got because we haven't down-regulated nitrogen fixation at all. So we've got too much nitrogen to try and get rid of. That's really what that graph is saying. Yep.
Yeah. Cool. So we'll move on to leaf metabolic energy. So leaf ME is changing over leaf biomass. So we have probably 12.5 to 11. So the range is quite small. So if we implement that into the model, this is what it looks like. And if we predict what it looks like for all the treatment, so 84 days and 42 and 28 days cutting, FD 2, 5, and 10 give a fair to good agreement. So for stem metabolic energy, it's very similar story. So we start from 8.5 to 6 when stem biomass reaches 3 tons. So also we have some outliers, which is from 84 days cutting defoliation treatment, some of them being senescent and some of them stand there for too long. So stem ME dropped quite a bit. Stem ME simulation results showed the fair to good agreement for all of the defoliation treatment and for dormancy classes. And from here, we concluded that leaf crude protein is about 25 to 33%, and stem crude protein is 7 to 27%. Leaf ME is 9.5 to 13, and stem ME is 5.5 to 10.5. And APSIM NextGen Lucerne model has a fair to good overall prediction of leaf crude protein, stem crude protein, leaf ME, and stem ME. The APSIM NextGen Lucerne model can predict forage quality, which will be very useful for on-farm pest management practices.
So just a comment for those of you from North America, we use ME here. It's the same as multiply. So if you multiply by 6.25, you get to digestibility is the figure here that we're dealing with. But interesting, all of the data showed what we would expect. The leaf ME stayed very high. It's hard to get more than about 3 tons of leaf biomass. At that point, you start to have some older dead leaves within your biomass sample, and that's we only get that when we had the 8-ton crops of lucerne that we were cutting, and the stem biomass could drop. The ME could drop very, very low as you get those wooden big plants as you're increasing. Yeah. So that's pretty much for this part. Are there comments on that? That's that's where we've gotten to with the data. This paper is in progress, and it'll depend on her new employers as to whether we get this one written up or not. But that's the work that we're doing at the moment.
Would you have expected some differences between the stem ME, for instance, for the different fall dormancies, or because that is something that we have sometimes observed, like for FD5 versus FD10, we sometimes find higher stem quality for FD5 compared to FD10. Is that something you have observed, or?
Not really. And if you go to your
stem ME,
the graph that you had for for Human, the one you produced for
Oh,
Human.
yes. Okay.
We actually didn't find any differences in the stems, and Human asked us earlier to look at the stem weight per centimeter, so grams per centimeter of the different height plants, and you can see they pretty much followed the same pattern. There's maybe something happening with the FT5s at the end there, but
it's probably a wrong data point,
Yeah.
because I extrapolate height, because during the cutting day we didn't measure the height, so I have to use the previous measured height to predict how much how tall is the plant when we defoliate it. So maybe a calculation error, but in general it doesn't show any difference.
we're seeing that some seasonal pattern in the weight, you know, the weight per centimeter, but not a lot of difference in the full dormancy rankings. Okay.
I have two comments. One is about the bad prediction of leaf nitrogen or leaf crude protein.
Yes.
Yeah.
My feeling is that because simulation, because if you add some treatment having an effect of nitrogen fixation, so you have a large variation of nitrogen content concentration in leaf due to treatment. But if your model is unable to account for this effect, you have this result.
Yes.
You have the predicted result for leaf where we have no effect on nitrogen, but in fact, you have a large effect due to the effect of treatment of nitrogen nutrition of the plant. So it's because the APSIM model is unable to take into account this effect on nitrogen fixation.
And it probably can, but we haven't imposed it yet.
Yeah.
Yes, you have to find the algorithm for doing that, but it's clear.
Yes,
So
and had it fit beautifully, we would have been upset, because if the fit was perfect, we would know that it's for the wrong reason, because we know everything else shows us the treatment is giving us a reduction in nitrogen fixation.
And we can see very easily that always the blue point are below.
Yes.
And some other due to, voilà. So you have a progress or a change to do in taking into account in APSIM model the effect of treatment on the plant nutrition itself.
Yeah,
it's the first point. The second point was about the metabolisable energy in stem.
Yes.
It is clear that you have a tendency here, not absolutely, but a tendency to have a decline in metabolisable energy as stem biomass increase. Here you have at the end you have a plateau, but this plateau is only obtained with a few data points. We cannot exactly what is, but you have a tendency to have a decline. So in literature, for example, to explain that some people said the stem of this variety is less digestible than this variety. But if the stem has big biomass, they have lower digestibility. So the growth itself, the growth of the stem itself imply a decline in digestibility, because the growth in height is also a growth in diameter, and the growth in diameter is due to the secondary cell wall deposition and is clearly lignin and hemicellulose deposition.
Yeah.
So
And
the more is the height, the bigger is the diameter, and the bigger is the biomass. So it's clear that you have here a fascinating, so as your very frequent cut as a result to shorten the stem, you have better stem.
yeah. And so, Jules, what we've done, this is a botanical separation between leaf and stem. But when we look at this from a quality perspective, from a grazing perspective, we actually separate the soft stem from the hard stem.
Yes.
And what we find is there is about 2.5 tons of high quality feed in a Lucerne stand, regardless of the yield. So all of our grazing management.
The five not fully elongated internode at the top are similar to leaf.
Yes.
The bad quality is at the bottom of the crop.
Yes. So our grazing management now is based on height.
Yes.
About 30 centimeters. We suggest 30 to 35 centimeters grazing. If you're cutting 40 to 45 centimeters, because you need that lignified part to actually get a cutter bar through and make hay. But our grazing management has changed completely to recognizing that lambs, for example, we bring it down to 25 centimeters. If we're direct feeding, they're on 25 centimeter feed, and that at the end of the season, the plant gets one good period of rest to recharge its underground reserves, and it's changed the whole dynamic of the grazing management for the systems that we're operating.
Sure.
I need to jump off, Derek, but I agree with Gilles on one of the comments that we have the same thing that we saw when we are looking at soybeans. We have the same problem with the leaf concentration. So very narrow variation, very narrow, and sometimes the model doesn't capture that, any variability on leaf. So it's a problem because the model is modeling fixation based on biomass, but we are seeing that, I mean, and we have a paper that we show that even under different biomass levels, your fixation can change drastically. So we are using more biomass as a proxy of fixation, when in fact we should be thinking about a different approach to, because it's not really just biomass, the point that you're driving fixation. And then I also agree, the last point on the stem, we have seen this, and Gilles knows this, on maize, the stem is a reservoir capacity. I mean, we have probably seen variability on maize going from 0.4 in concentration to almost 1.6, 1.8. So we are talking about variability on concentration in a stem fraction. I mean, that is 400%. And I think that what you are seeing is exactly right. So, I mean, excellent data. I mean, very exciting. For sure, there will be a lot to be done with in the future.
Good. I'm hoping it was useful for you, Ignacio.
Yeah. I'm glad to connect with some of the Argentinian fellows too. So hopefully you have a good presentation, and we'll be in touch. Thanks, Eri, for inviting too. Thanks, and congratulations, Jan, for the work. Excellent.
Thank you.
Okay. Thank you.